We'll begin our tour of the advanced lab with X-ray physics. That's this experiment. That's appropriate since the first Nobel Prize in 1901 went to William Conrad Röntgen for the discovery of, well, the citation says, the remarkable rays subsequently named after him, not the mention of X-rays, which came sometime later. There were at least 5 other Nobel Prizes in the 100 years now devoted to X-rays in one form or another. Some say that soon another Nobel Prize will go to X-rays for the invention of the X-ray free electron laser. Here at ASU, we have a very strong effort on a novel concept of a compact X-FEL instrument led by a team of people including Spence, Graves, Kindle, and Froma. In this experiment, we'll do several different things. We'll take an X-ray image, like a dentist image. We'll use Albert Einstein for our first patient of the day. We'll do a computerized tomography or CT scan, which you may be familiar from the medical context. We'll do a Bragg diffraction from a sodium chloride crystal, and we'll look at a Lowy pattern also from the sodium chloride crystal. X-rays are widely used for crystallographic measurements, that is, determining the atomic structure of materials, most notably recently for biomolecules, in particular the COVID virus that causes the infection. So that's X-ray physics experiment. This experiment is the famous double-slit experiment from Thomas Young, 1801, 100 years before the Nobel Prizes even began. His experiment proves that light is a wave because it goes through both slits at the same time to create an interference pattern. In our experiment, we'll go beyond that and do what I'd like to call photon diffraction. So we turn down the intensity far enough that we can count the individual photons with a photomultiplier tube. That proves that light is a particle that goes through both slits. So this is the fundamental puzzle or mystery of quantum mechanics, that light travels as a wave but arrives as a particle. This is the Zeeman experiment. Nobel Prize 1902 to Pierre Zeeman for discovery of spin on the electron. At the time, that's the missing quantum number. Of course, we know now that determines all the quantum properties of statistical mechanics, of fermions and bosons, and everything that implies. So in this experiment, we'll use a cadmium lamp that's inside the pole pieces of a strong electromagnet. That provides the quantization axis, comprising spin up or spin down in this case. And we'll look at the spectral lines through a Fabry-Perot spectrometer on the optical rail over there. Here's an example from the Fabry-Perot, and the splitting of the rings is the splitting of the magnetic energy, mu dot B. We can look at the spectral lines in 2 orientations from the magnet by turning the magnet table, and we insert polarizers to look at different components of the line. This experiment is the interferometer. That was a Nobel Prize in 1907 to Albert Michelson. The citation for his prize says, for construction, invention of a precision optical instrument. They did not measure his famous result of measuring the speed of light with and against the Earth's motion, which was called the most famous null result in science, and ushered in the special relativity and the beginning of the quantum age. His citation does not mention the speed of light at all, partly because it was still a controversy amongst the leading scientists of the time. In this experiment, we'll build a Michelson interferometer, and we'll use it to measure the refractive index of air and of a glass plate. We'll also build a Fabry-Perot interferometer, which is widely used in many scientific instruments. The Michelson interferometer is famous recently from the LIGO experiment, laser interferometry for gravitational observations. It was a combination of Michelson plus Fabry-Perot that had a sensitivity of 10 to the minus 21 in the strain of the interferometer. This is the most sensitive instrument ever built anywhere, anytime. So interferometry from Michelson to LIGO. This experiment is the Compton Effect, Nobel Prize 1927 for demonstrating the inelastic scattering of X-rays. In this experiment, we'll use a radioactive cesium source that generates gamma rays of 0.7 MeV. The experiment consists of, well, you see it setting back here behind a wall of lead bricks that are conveniently placed at waist height. That reminds us that we need to be careful about how we handle X-rays. The experiment is done by placing the cesium source in this collimator. We put that on an angle control. The gamma rays hit an aluminum target and scatter into a photomultiplier tube. And the measurement consists of showing the energy shift versus angle for the scattering of the gamma rays and shows that that scattering occurs exactly as the scattering of billiard balls against each other. This experiment is the helium-neon, or HeNe Laser, Nobel Prize 1964, Charles Townes et al. There have been at least 4 other Nobel Prizes related to laser since then, most recently for quantum optics and ultra-fast light pulses. In this experiment, you build a HeNe laser with a helium-neon tube right here using external mirrors that we adjust to align the laser. And we'll measure the spectral properties with the diffraction grating and with a Fabry-Perot spectrometer to measure the cavity modes of this laser. This is the Hall effect, Nobel Prize in 1985, Klaus von Klitzing, for demonstrating and discovering the quantized Hall effect. So we're familiar with current voltage relation of Ohm's law, where current is linear proportional to voltage. In the quantum Hall effect, that's not true. The conductance varies in quantized steps of E squared over H. This provides a relatively simple way to measure those fundamental constants to 1 part per billion. In this experiment, we'll measure the normal Hall effect with germanium samples. We'll put them in a magnetic field over here, and we'll measure the Hall conductivity of those materials versus temperature and field. The Hall effect in that form is widely used in the semiconductor industry to determine the concentration of N-type or P-type carriers in semiconductor materials. We'll end our tour of the lab here with an experiment on quantum entanglement. This is an experiment that explores the continuing mystery of quantum mechanics. I think it was Feynman who said, if you think you understand the photon, you don't know enough about it. In this experiment, we'll make an entangled pair of photons, converting 1 blue into 2 reds that are coupled or entangled. In 1985, Einstein, with Podolsky and Rosen, wrote a paper that's known as the EPR paradox, in which they explained that actions cannot happen at a distance instantaneously. They described the belief that the universe exhibits so-called reality. That means that a photon exists regardless of whether somebody is observing it, and locality. There is no instantaneous action at a distance. Turns out the universe exhibits neither of those properties. And we're going to make measurements that demonstrate that. It's an exquisite piece of instrumentation that, as I say, generates the entangled pairs of photons with a powerful laser on this end. They wrote everything into fiber optic cables so it's safe and can actually be measured in room light as we have here, so we can count individual photons safely. So we'll measure, over here is an apparatus which is a Michelson interferometer with this apparatus, which is wonderfully built for demonstration purpose, very user-friendly. It also provides real numbers, so we can do actual experiments with numbers to demonstrate the EPR paradox.